All right, we're back with part 2 of our lesson 2.2, where we're looking at Punnett squares and inheritance. So this part 2 is on sex-linked traits. So up until this point, we've been looking at examples of autosomal inheritance, is what this is called, when we're only looking at the chromosomes or genes that lie on chromosomes 1 to 22. So up till now, we've been ignoring the X and the Y chromosomes. And there's traits on those chromosomes that what we call and we refer to as sex-linked traits or sex-linked inheritance. Okay, so most cases of sex-linked linkage inheritance that we're going to be looking at, especially, are on the X chromosome. Where on the Y chromosome, because it's so much smaller, you can see the Y chromosome here, it's much smaller than the X chromosome. There's not even an allele located on the Y chromosome for the specific trait that we're looking at. So it's whatever the female has or the X chromosome has that is actually going to be expressed. And there's a few rare cases, just mentioning here, that there is an allele on the Y chromosome that only if you have that Y chromosome, you would be able to express that allele. So the example here is hairy ears, and yeah, there's a great picture. All right, so let's take a look at some sex-linked traits. One very common example of a sex-linked trait is hemophilia, which we talked about earlier in the unit. And this is the inability or the disorder where you have blood clotting issues. You're not able to make scabs, right, or stop bleeding when you're getting a cut. It's a life-threatening disorder, and this is all found. The gene for this is found on the X chromosome. So the female is carrying or not carrying, but the female is the one that determines their genetics is going to determine who of the offspring are going to have hemophilia. So let's just look at, first off, how these sex-linked traits are written. So first thing you're going to write is the chromosome. Okay, so when you are dealing with a woman, you have an X and an X chromosome, right? So a woman has to have 2 X chromosomes. A man has to have an X and a Y chromosome. And typically we write the X first. Okay, so it doesn't matter. If you're male, this is your genotype. If you're female, this is your genotype. Capitals. Okay. Now, when we're looking at traits that occur on these sex chromosomes, we still use those capitals to represent dominant and recessive, but we put them up at the top of these alleles. Okay, so you can see there's an example here. So hemophilia is recessive. Okay, recessive. So the dominant alleles give you a unaffected female. So no hemophilia, not hemophilia. So if the female has 2 dominant alleles for hemophilia, they're fine. Okay, it's not the disease. If the female has 1 dominant and 1 recessive is actually the one that causes the disease, but as long as they have 1 dominant that's healthy, that dominant is going to overpower the recessive and they will be fine. They're unaffected, but we call them a carrier. So that would be the female carrier. So they have 1 of those recessive alleles that cause the disease. So the only way a female is going to get hemophilia is that they have to have 2 recessive alleles, 1 on each of their X chromosomes. Okay. As opposed to a male. Okay, so a male, remember on the Y chromosome, there isn't even the allele for hemophilia. It doesn't even exist there. Okay, so you don't even have one on the male, but the female has the chromosome, the allele, for hemophilia, and in this case, it's the dominant, normal, no hemophilia gene. So this would be the X chromosome of the male has the dominant one, so it's totally unaffected, fine, no problem, that man or that boy. This genotype here, you have the X chromosome that contains the recessive allele for hemophilia, and there's nothing to block it. There's no dominant allele that's going to hide that expression of that disease. So this male will have hemophilia. Okay, so that male is gonna have hemophilia, and this female is gonna have hemophilia. So it's actually a lot more common for men to have hemophilia because they only need to have one of these recessive alleles, whereas a female would have to have two. That would mean her dad, because this female, one of her X chromosomes had to have come from her dad, right? And one from her mom. So it could have been a carrier. So mom could have been a carrier, but you didn't know that, right? Because the mom didn't have the disease expressed. And then the one from her dad would have had to have had hemophilia for this female to have hemophilia. Okay, so it's very rare for females to have hemophilia because these males, typically the lifespan of a person with hemophilia is not very long. Well, in the past anyway. All right, so let's move on to the next page. There's some more examples here. Oh, so this is good because this diagram really shows this pattern of inheritance. So you have a man here, father, X and Y chromosome, one of each, and his allele here is showing that it's a normal allele, it's unaffected, does not have whatever disease we're talking about. Here's the mother. She's got one X chromosome with the gene that's normal, fine, no disorder. And then this, she's a carrier. Okay, she's a carrier. Oh, there it is, carrier of that disease or disorder, whatever it might be. So we're going to watch what happens to her chromosomes and the father's chromosomes and how they mix. So if the father is going to have a male child, the only way you're going to get a male child is if the father donates, or the gamete from the father has the Y chromosome. That's the only way you're going to get a Y chromosome to an offspring, is if the father. So it's actually the father's gametes that determines the sex of the child, if it's a female or male. All right. So the Y doesn't have any of this disorder or disease on it, so that's unaffected right now. So both of these boys have become boys because the father has passed on a Y chromosome and didn't pass on the genetic disorder. Now, both of these boys, their X chromosomes had to come from mom. So in this case here, this X chromosome came from mom, and you can see it's the X chromosome that has a little red on it, so it's the normal chromosome. It's fine, no disease, so he's unaffected. He's good. But this boy here, this son, got the X chromosome here that has the affected gene, whatever it might be. Okay, if it's hemophilia or whatever. But he's been affected. He's going to have that disorder. He's going to express that disorder. Female, though, you can watch now. So to have a daughter, that means that the father has to have donated, or the gamete from the father has to have been the X chromosome, and his X chromosome was fine. It's unaffected, so that daughter is okay. And in this case, this unaffected daughter had the X chromosome from the mom as well, which was unaffected, so she is fine. She's not even a carrier of the disorder. Now, this other daughter, so she is also getting the X chromosome that's unaffected from her father. She has to get the X chromosome from her father, right? She can't get the Y because that's how you get a son. And then from mom, she is getting the affected X. So she is getting one normal and one affected X chromosome. But because she's got one of these normal ones and it's dominant, it's going to overpower this. So she'll be fine, not affected, but she's a carrier, right? So she's a carrier like her mom. So in the next generation, she could pass on the defective gene. All right, so that kind of gives you an idea of how these chromosomes are passing around and how these traits, it's kind of an interesting thing. So if you look, it's here, it's only the son that's actually going to have the disorder in this case, right? So that's why they tend to be more common. So if you start to see a disease or a disorder that shows up in a pedigree, and which we'll talk about later in a family tree, a lot more in males, then it's probably a sex-linked disorder. Okay, so 50, so you get, every time you have, you do a Punnett square kind of thing, you are going to get 50% chance you're going to have a male, and 50% chance you're going to have female kids. Okay. Why is that? Well, if you have the man and his gametes are X and Y, and you have the female and her gametes are XX, you do a Punnett square here, you're going to get XX. We're leaving out any kind of disorders in this case, just to show you how sex is determined and orients itself, expresses itself. So here, 50% in both of these are females. So 50% of the offspring are female, and both of these are males, and 50% male. So when you have a child, right, 50-50 chance whether it's male or female. And then in this case, if you're just talking about the boys, the male offsprings, in this case, 50% of the males are going to have the disease, would have the disease, and 50% would be fine. If we're just talking about the males. All right, so moving on. All right, let's try a little practice problem here. If you're watching the slides, you can just watch the video solution. Otherwise, we'll do the solution together here. So hemophilia is an X-linked recessive trait, right, that affects blood clotting. If a carrier woman and a hemophilia man have a daughter, what is the percent chance she will have hemophilia? So let's figure out what a carrier woman's genotype is going to be. This is where you could pause the video and see if you can figure this out. Figure out what the man's genotype is and what the woman's genotype is. And then we're going to do the Punnett square. So pause and figure that out. And then come back. Okay, here we go. So a carrier woman. So carrier woman. So we know it's a woman. So she has to have 2 X's. If she's a carrier and the trait is recessive, one of the alleles on the X chromosome is recessive and is for hemophilia. And then the other one is going to be dominant and not cause hemophilia. Then we have the father. A man always has an X and a Y. Hemophilia is not carried on, or there's no allele for hemophilia on the Y-axis, on the Y chromosome, so we ignore that. And this man is hemophilia. So he's got hemophilia. So to have hemophilia, he has to have the recessive allele. There is our mom and our dad and the possible gametes that they're going to give. So we're going to turn this into a Punnett square like that. Alrighty, so let's do this. I'm just going to bring from the top down first. So we're going to have from the mom, X capital H, from the dad, X little h. This daughter, 2 X's, right, has 1 gene for hemophilia, but also a dominant one, so she's a carrier. This daughter, here we go, X little h and X little h. This daughter, 2 recessive alleles, she has hemophilia. Right? All right, let's check out the sons. How do we know they're sons? Because they're getting a Y chromosome from dad. And this one's going to have a dominant gene from mom, so they won't be affected, this boy. And then from mom, this boy is getting the hemophilia gene, which is recessive, but there's nothing to counteract it because he has the Y. So this son is going to have hemophilia. So to answer the question, daughter, what's the percent chance that the daughter will have hemophilia? So when it's specifically asking about the percentage a daughter will have, we only look at the daughters, at the females that are produced, and half of the females, this half, are going to have hemophilia. So 50% of daughters. Right? Same thing with the boys, actually. So with the son, if the question was what percentage of the sons, it's going to be 50% of the sons as well. Alrighty. Another example of a sex-linked trait that you'll come across in some of the problems is color blindness. So these are genes for pigments found responsible for perceiving the red and green color, and these are found on the X chromosome. So again, because it's a sex-linked trait, this tends to be more common that men have color blindness than women. And there's some tests if you want to go check. If you can't see what number's in that circle, you might want to go check this colorblind test. Sometimes people don't find out until much later in life, like your age right now, that they're actually colorblind. So it's actually kind of interesting. Can you see the number here? If you can, yeah, it's a 5. If you can't, then go check out that colorblind test. Alrighty. So again, the color blindness gene is only carried on females, and here are the genotypes that a female could have. Female could have 2 of the normal genotypes. So again, the recessive allele is causing color blindness in this case. And the only way you're going to get it as a female is if you have 2 recessive alleles. So that would be the genotype for a colorblind female. So a carrier, there's a carrier. The carrier will not be colorblind in this case. Male, we have a normal male and a colorblind male. So males, can a male ever be a carrier? Well, if a male has the colorblind gene, he can't hide it. Right? He only has 1 X chromosome, so there's nothing to hide that gene because there's no no allele on the Y chromosome. So he cannot be a carrier. Males can either be normal or colorblind. That's it. They have no option of being a carrier with a sex-linked trait. All right, this video here is a great review. If you want to go over all of heredity that we've been doing in this lesson so far, I would highly suggest it. And this is just a list of our references for this video. All right, have a great day.